Okay, so our last speaker for today will be Elliot Gathercole. He will, from Lancaster University, will speak about Superheavy Skeleta for non-normal crossings divisors.
Thank you for the invitation to speak. So I will start with a motivating example of one such skeleton. So in the product P1 times P1, if we equip each sphere factor with the standard action angle coordinates, and then we take the pre-image of the two perpendicular lines pictured, then we get an embedded Lagrangian Klein bottle, which we will denote K. And so the question I'd like to answer is, what can we say about K with respect to rigidity? So for example, can it be displaced from itself by a Hamiltonian isotopy? And what I'm going to outline the proof of is, in this case and for other related examples, is that this K is super heavy with respect to the identity in quantum cohomology. I will explain a bit more what that means later. So when we have a projective variety and a divisor, which is in the anticanonical class, or where we can scale things by rational numbers, so in a multiple of the anticanonical class, and the convention that we are going to use is that D is in 2 times the anticanonical class, then we can get from that a monotone symplectic manifold, or give M the structure of indeed a Kähler manifold, which is monotone, and the complement of D becomes a Liouville gets a Liouville structure up to a certain notion of equivalence. And in this Liouville manifold, we have the Liouville vector field, and we have the skeleton, which is essentially a subset of all of the points which do not flow towards D as we flow outwards along this vector field. And so the example K that I have shown you is the skeleton of such a divisor complement with the complement of the divisor pictured here, this union of 2 1-0-degree curves and one 1-2-degree curve, where in particular one of the curves has weight 2 and the others have weight 1. And the reason why this might be useful is because if instead of something that looked like this, we had an orthogonal SC divisor, which is a union of orthogonally intersecting symplectic submanifolds, and in positively and orthogonally intersecting symplectic submanifolds, then we could apply this theorem of Ullmann, Sheridan, and Farrell-Gunez, which says that the complement of that kind of divisor has a skeleton which is SH full, which is the same as being full measure with respect to the measure that Adi described in the previous talk. So that would definitely imply being non-displaceable from itself. And the way that the proof of that goes is roughly to every smooth embedded divisor component, you assign an embedded symplectic tubular neighborhood, and on each of those you have a standard U1 action, and that action is Hamiltonian, and if they can be arranged to be compatible along the intersections between submanifolds. And so at every k-fold intersection you have a Hamiltonian k-torus action, and then you use these Hamiltonians to make a Hamiltonian on your whole space, which inherits, which in the periodic orbits of this Hamiltonian, we want to inherit properties from these circle actions, and then use those Hamiltonians to compute the invariance we want. So obviously that doesn't work in the case of this divisor of which K was a skeleton of the complement, because in particular the components don't intersect transversely. So the intersections between 2 components in that case are locally modeled on this intersection of y equals 0 and y equals x squared in C2. So instead of trying to construct these tubular neighborhoods and making sure they're compatible along the intersection, we can notice that there is another Hamiltonian circle action which fixes the intersection point and preserves these 2 components of D. And then if we can construct in a similar manner to the SC case these tubular neighbourhoods for the smooth curves, which are the divisor components, and we want to arrange them to be compatible with this circle action near the singular point. So we do get, so near the intersection between these tubular neighbourhoods and this ellipsoid surrounding the singular point, we do get a Hamiltonian torus action, but it comes from our pre-made circle action and one of the U1 actions. So the important thing is we don't have to care about the compatibility between the U1 actions for these two tubular neighbourhoods. And as in this SC divisor case, we want to extract some numbers from these circle actions, which we then use to prove things about the Hamiltonian that we're going to construct. So if we consider one of the orbits of this circle action in this neighborhood of the origin in C2, and we consider a small disk that has as a boundary a1 periodic orbit of that action, then we can find the action of this arrangement with an orbit and a cap, which is given essentially by the intersection number of that small disk with the divisor D, which in this case is 6, because we have intersection number of 1 with each component, and each component, and one of the components has weight 1 and one of the components has weight 2. So sorry, rather we have intersection number of 2 with both components because the projecting onto the factor that's perpendicular, it's wrapping around twice. And we can find from the Zehnder index of this capped orbit, which is the other thing that we need, which we can just calculate because it is a standard fact about this representation of U1 on C2. And you can see that these two numbers are the same, and this is analogous to the condition of this theorem, which where we needed the weights of the individual components to be less than or equal to 2. Because if these were just if this, instead of this funny circle action we were talking about, the standard U1 action, the Conley Zehnder index would always be 2, and this action would just come from the coefficient of the respective divisor component. So we have the analogous property here that we need to prove things with these circle actions. So the next step in both the proof in the SC divisor case and this case is we use these radial Hamiltonians to construct a family of hypersurfaces around the divisor D, and then we construct a Hamiltonian rho by setting this hypersurface to be a level set and then extending them along the flow lines of the Liouville vector field by setting rho to be exponential in that direction. And this will ensure that we can relate all of the orbits of, or all of the Hamiltonian orbits generated by rho to things that are made from this circle action in a neighborhood of this divisor. So we're going to use this, we want to use this Hamiltonian to prove this property called superheaviness, which is so for each Hamiltonian H, we get this number zeta, which is to do with how a certain spectral number of which we get from the associated Hamiltonian flow cohomology changes as H is rescaled by some factor. So using these properties that we found for rho, which relates the Conley Zehnder index of these capped orbits to the action, we get that if we used a Hamiltonian which was a function of rho, it effectively gives us the property that we want, and then you have to use the argument about the monotonicity of this to say that we can bound any Hamiltonian by one of the form that we want. And it just to note that this property is possibly stronger, but definitely implies being SH full. So in other words, this does answer the question that we wanted to answer, because it implies essentially that this Lagrangian intersects everything that shows up with respect to relative symplectic cohomology. So that was one situation, and obviously it would be nice to know something about some other cases. So the things that we used there were, first, we have this stratification of D into embedded submanifolds of various dimensions. So we split up this divisor into some curves, and then the singular points, which were their own strata and needed their own radial Hamiltonian. And then we want a radial Hamiltonian that cuts out each of these strata, which generates a Hamiltonian circle action. And then I suppose the difficult thing is that we want these Hamiltonians to commute with each other when they need to. So in this picture down here, we have this neighborhood of a point, and if this point was one stratum and this line was another stratum, because any neighborhood of the line will intersect the neighborhood of the point, we need some little neighborhood where those two Hamiltonian circle actions commute. And in general, we might not get that the skeleton is super heavy because we have different numbers coming from these Hamiltonians. From this data of this radial Hamiltonian for every stratum, we get this number of the action and the index with respect to some cap, and then we take a maximum of this quantity over one periodic orbit for every radial Hamiltonian and the correctly chosen cap, and then this number gives us a sublevel set of these Hamiltonians, and then we use a similar argument to this to prove that that subset is super heavy. And in particular, if this number sigma crit is 0, then we get, as in the example of K, that the skeleton itself is super heavy. So the difficult bit here is not really the difficult bit here is actually getting these radial Hamiltonians and ensuring that they are compatible in this way. And one way that the previous example would be generalized is if you have a divisor where all the singular points have a form like this, where we have some local holomorphic coordinates with a C star action with some weights on our coordinates, such that the divisor is cut out by a polynomial which is homogeneous with respect to those weights, then we can use that C star action to construct a U1 action, which we can use in the same role that we used this action. And one possibly interesting thing, so that gives you a radial Hamiltonian for the stratum, which consists of a singular point. And then for the smooth parts of the divisors, we can use a Moser argument with a group action, so to try and at every stage keep everything equivariant in the right way to construct a radial Hamiltonian for the smooth parts of these divisors, which will commute in the right way. And so unlike in the case where the divisor was of this SC form, we are not just getting this does not just depend on information about what cohomology class is represented by each component or what weight we gave each component in the divisor. There is additional information that depends on local behavior near the singular point. So, for example, if we had a singular point which was modeled on this polynomial, we would get this contribution of n minus 2 times a plus b over n to this number, which is going to tell us what subset we can say is super heavy. And this applies in the case where essentially we have a top level stratum, which is the smooth part of your divisor and also a singular part which is itself an embedded manifold, because the difficulty is in ensuring each upper stratum is compatible with the lower stratum. So here we have a lower stratum which we're getting, one lower stratum which we're getting for free, and then we can construct the higher strata using a Moser-Klein type argument. And so, as well as when the divisor is some curves, we can this argument also applies to algebraic surfaces where the singular points are all of ADE type, because they can also be modeled by something that looks like this. So, sorry, how much time do I have?
About 5 minutes.
5 minutes, okay. So one example where we do not get sigma crit equal to 0, but we get a neighborhood which is super heavy, is if we take our ambient manifold as of three-dimensional projective space, and we take our divisor to be the cubic discriminant locus, then the complement becomes the quotient of SL2, and inside it we have a Lagrangian skeleton, which is the corresponding quotient of SU2, which is known as the Chiang Lagrangian. And in this case, the discriminant locus has inside it a smooth embedded curve, the twisted cubic, which is its singular locus, and then the rest of the curve is smooth. And if we take a sort of normal slice to this twisted cubic, then the intersection of that with this divisor looks like the standard cuspidal cubic curve. So geometrically, it looks like one of these quasi-homogeneous examples. And you can actually get this group action from the SU2 action on the whole space, but geometrically it looks, with respect to all of the properties that we need, it looks the same as this case with A equals 2 and B equals 3. So the answer we get is, or rather the output we get, because this curve is itself anticanonical, the smooth part doesn't contribute to this number, and instead this singular stratum is the only thing that gives a non-zero contribution. And so we get not that the Chiang Lagrangian is super heavy, but that a neighborhood of it, of volume 1/6 cubed of the total volume of M, is super heavy. And that is about everything. So thank you for listening.
Thank you. Are there any questions?
I can ask a question.
Yes, please.
So, I mean, this is not directly related, but there is some other, there is this like Biran decomposition. Balls have to intersect the skeleton type results. Like if you embed a ball that's large into CP2, then it must intersect this skeleton, like the other side of a quadric, for example. Do you know this story?
I don't believe so, no.
Okay. I just was going to ask, like, does that story kind of extend to this thick, super heavy versions of Skeleta? Like, do you get intersection phenomenon between balls and this kind of neighborhoods of Skeleta somehow?
I can't imagine. If the balls are too small to sort of appear with respect to these invariants, then I can't see how to go directly from this result to an intersection result like that.
Okay. Thank you. It's a nice talk.
Could you recall the assumptions on your theorem? Not the one on the client bottle, but the one which is more general. Because I was confused during the.
So the most general assumption is the existence of all of these radial Hamiltonians which commute with each other. And then, so there's another step which is constructing those. And so the most general setup that I have written down is you have some action for your lower dimensional strata, which you get from the algebraic structure, and then for the top level structure, you can always do something. So I suppose when the singularities come with a C star action and are smooth themselves.
Okay, thank you. Are there any other questions? Okay, so thank you very much.